Section 25. A terse history of our universe. This chapter is a terse version of the prior chapter. It is in time order, but times, temperatures, and scale factors are not given. This can be a useful quick read or to challenge yourself to put times or temperatures on events or epochs, or you could rearrange them and try to put them in correct order. Have fun with it. First, there may or may not have been something before the Big Bang, but we can never know. Then there was something, the chaos of quantum gravity at the Planck time and Planck energy. Then gravity weakened and general relativity was valid. Electroweak interactions became weaker than the strong nuclear force. Inflation, inflation, inflation. Our observable universe became flat and pretty uniform. Radiation got reheated. Radiation particles were different then than later or now. All particles had zero mass then. There were quarks and gluons and color charge. Radiation dominates expansion, which is decelerating. Radiation temperature falls as the universe expands, as does the energy density and pressure of radiation, and later, matter. The radiation particle energy fell below the mass of the Higgs boson. The Higgs field turned on and gave other elementary particles their mass and their electrical charge. Ordinary matter elementary particles and forces then had the same properties and values as they do today. There were photons, neutrinos, electrons, and quarks as we know them today. The weak interaction became much weaker than the electromagnetic force and extremely short-ranged versus the infinite range of electromagnetism. Quark-antiquark pairs stopped being produced. The quark-gluon plasma evaporated to produce distinct baryon particles. Antiprotons annihilated with protons and antineutrons with neutrons, but somehow a 1 part per billion residue of protons and neutrons remained. Muon-antimuon pairs ceased to be produced and annihilated. Neutrino-antineutrino pairs ceased to be produced, could no longer annihilate, and their interactions with other matter became extremely rare. These cosmic neutrinos and antineutrinos have been traveling the expanding universe at near the speed of light. Physicists might be able to directly detect these cosmic neutrinos on Earth in the next decade. All neutrons became bound with protons, leaving hydrogen and helium nuclei with a smaller amount of deuterium and lithium. No carbon or oxygen were formed. Electron-positron pairs ceased to be produced and annihilated, but somehow a 1 part per billion residue of electrons remained, exactly matching protons, and the universe is electrically neutral. Scientists do not know what cold dark matter consists of, when it was created, or if it has ever interacted with light, ordinary matter, or itself, other than through gravity. But it is believed to not be interacting from at least this time forward. The energy density of radiation fell below the energy density of matter, and expansion of the universe is then dominated by non-relativistic matter. Expansion continues to decelerate. The universe changed from an opaque plasma of ions and electrons to neutral atoms and transparency. Photons traveled the universe unimpeded. Light that was orange-red at that time is now microwaves. Light redshifted from visible to infrared, and the universe was dark. Slight overdensities of dark matter contracted. Slight overdensities of ordinary matter contracted. The first stars formed and shone visible and ultraviolet light. The diffuse gas of hydrogen atoms throughout the universe ionized from the star's ultraviolet light, but the universe remained transparent to infrared and microwave radiation. Galaxies formed, with supermassive black holes at their cores. Quasars shone brightly. The energy density of matter fell below twice the energy density of dark energy. Expansion then accelerates. The energy density of matter fell below the energy density of dark energy, and expansion of the universe is then dominated by dark energy. Expansion will become exponential in future. Cosmic microwave photons are as common as dirt, more numerous than photons from starlight from galaxies. Our future will probably be big chill, where distant galaxies appear dimmer and redshift into the infrared in future. Or our universe could end with a big rip in hundreds of billions of years, ripping all matter apart at a finite time, where the scale factor goes to infinity, or beyond present physics. Or there could be a big rip phase, followed by a big chill. But it is unlikely our universe will contract to a big crunch.